continuation of what we covered yesterday. Okay, so yesterday we talked about different types of transformations that we could do for our parabola, right? So we talked about stretches and compressions, where we're kind of stretching out the parabola or squishing it down or reflecting it across the x-axis. And then we talked about translations, right? So translations we saw just move the parabola left, right, or up and down. And we noticed that at least with the translations, that actually affected where our vertex was going. And now that all leads us into what we're discussing today. So today we are introducing what's called vertex form, right? And vertex form is important because it tells us where the vertex is, right? So we'll be doing that, and then I have a couple little word problems, and then that is it for the week, okay? Yesterday, again, as I mentioned, we saw 3 different types of transformations. Today, our job is to put all of those transformations together. So we're going to be dealing with reflections, stretches, compressions, translations, everything all in one go, okay? Here is the general form for a quadratic expression written in vertex form. So this joins us, or this joins with, we had y equals ax squared plus bx plus c. So we had standard form. We're introducing vertex form today. And last chapter, we spent a lot of time talking about factored form, right? Y equals a, x minus s, x minus t, okay? So our ultimate goal between now and the end of quadratics is to be able to convert between all of these various forms. That's our main mission here, okay? But today we're just getting used to vertex form. We'll talk about word problems for expressions that can be written in vertex form. So let's try a little graphing exercise. So my goal here with this first example, I want to graph 2 times x minus 3 squared minus 8, and I'm going to be doing that by applying the transformations that we discussed yesterday. But just to make it a little bit more visually apparent, what I'm going to do is I'm going to apply one transformation at a time. Or actually, I'm going to apply like the stretch and compression first, and then I'll apply the translation. So I'm going to put together the 2 translations, but the stretch and compression I'm going to do first. Okay, so let's give this a try here. So my first job is to just plot y equals x squared here. Okay, so I always like to come up with a little t-table or a table of values. So x, y. For my parent graph, for my just y equals x squared, I always just pick the same 5 points. So 4, 1, 0, 1, and 4. And so let's plot these. So 0, 0, negative 1, negative 1, 2 and 4, negative 2 and 4. And then you just connect the dots here. Okay, so there's my basic untransformed parabola, okay? Now, I'm going to apply my vertical stretch. Now, one thing to keep in mind when you are doing these transformations is that it is important that you always apply vertical stretches, reflections, vertical stretches or compressions, and reflections first. So apply vertical stretches, compressions, and reflections first before translations. Okay. The reason being is if you start moving the parabola around first and then you apply a stretch or compression, it's going to throw things off a little bit. Okay. So who remembers what this stretch is going to do? How does this affect our graph?
It's gonna like stretch is a bit like yeah, so you're basically like taking the ends of the parabola and like pulling them apart.
Yep, good.
By however many units.
Yeah, so this is a vertical stretch, you're right about that. And the way that you want to think about it is indeed you kind of hang onto the vertex and you grab the ends of the parabola and you just pull them apart, right? This causes the parabola to get kind of like skinnier in the horizontal direction. Does anyone remember what happens to the y values when I do something like this?
They change.
They definitely do change, yep. Do you remember how they change?
Well, I think this one will be by 2.
Yeah, and in this case, because it's a vertical stretch, we're actually going to multiply by 2, right?
Yeah.
When we deal with translations, then we're going to be adding and subtracting, but stretches and compressions, they're all about multiplying or dividing, right? So in this case, a vertical stretch by 2, or by a factor of 2, whatever terminology you want to use, what that's telling us to do is it's telling us to multiply all the y values by 2. So multiply y values by 2. Because that's what a stretch does, right? A stretch multiplies all of the y values by 2, but the x values remain the same, right? So I'm going to carry through my same x values. But then I'm going to take my original y values, so 4, 1, 0, 1, 4, and multiply them all by 2. So I'll have 8, 2, 0, 2, 8. 8, 2, 0, 2, 8. And then I can go through and graph that, right? So 0, 0 still remains the same. Let's use a different color here. So 0, 0. But then I will have negative 1 and 2 and 1 and 2. And I will have negative 2 and 8 and 2 and 8. So there's my new parabola there. So I've applied my vertical stretch. Okay, not bad. A little bit wiggly there. I'll probably do it slightly better here. Okay, not bad. A little bit better. And so we can see indeed, comparing these two graphs, that the vertical stretch has caused my graph to get like a little bit squished in the horizontal direction, or a little bit stretched out in the vertical direction. Okay, so far so good. Now we have to take care of the translations. So again, remember that when we're dealing with something like this, the translations come from this -3 and this -8. Okay. The only thing that we have to be really careful about here is whatever sign is inside the brackets. So even though it says like -3, what we're going to be doing is adding 3 to all of our x values. So we're moving 3 units to the right. So this will be 3 units right. And this will be 8 units down. Okay. So when we take care of the horizontal and vertical translations, right 3 units implies that we're taking all of our x values and we're just adding 3 to them. Okay. The translation down 8 units, again, we're taking whatever our y values were and we are subtracting 8 from them. Okay. And I'm going to do that with the table of values that I got after I did my stretch, right? So essentially, this is my table of values as it stands now. And now what I'm going to do is I'm going to take all of the x values and add 3, and all of the y values and subtract 8. And I'm going to come up with a new table of values to plot. So x and y. So I'm going to add 3 to all of my x values. So that'll be 1, 2, 3, 4, 5. And then I'm going to subtract 8 from all of my y values. So 0, -6, -8, -6, 0. Okay. And now I have another table of values to plot here. So 1 and 0 right there. 2 and -6 right there. 3 and -8. So 3 and -8 right there. 4 and -6. Now the pattern just repeats. 5 and 0. And there is our new translated parabola. Okay. And of course, when you're like when you've plotted it, or I guess after you've plotted it, you can always go to Desmos and kind of check it out, right? So let's see what happens when we try that here. So let's see how well we did, I guess. So here we had y equals 2, x minus 3 squared minus 8. Okay, not so bad, not so bad. So again, the vertex is at 3 and 8. That's where my vertex is located. We have an x-intercept at 1 and 0 and 5 at 0. So 1 and 0, 5 and 0. So it seems like I've done a fairly good job here. Okay. And again, so looking at the equation here, y equals 2x minus 3 squared minus 8. With these two values, it actually will tell us where the vertex is, right? That's why vertex form is so useful. We know, even before graphing this, we know that the vertex has to be at 3 and 8. 3 and negative 8, right? And so that's actually really helpful, right? Because even before graphing, I can kind of use that as a check for when I eventually do get my graph to make sure that the vertex is in the right spot. Okay. Any questions about how I graph that? Okay, cool. All right, let's try one more example here. Same idea. Although this time we have a reflection, so a little bit different, but the way that we approach it is kind of the same. So again, I'm going to start with just my basic parabola here. So let me just go and copy the table of values. There we go. So this pattern never changes, right? So this is just something you can remember if you would like. So negative 1, 1, 0, 0, 2, negative 4. So there's our standard y equals x squared parabola. Okay. Now when we're applying our, this case, we have a reflection and a stretch. Actually, let me make this larger again, sorry. In this case, we have both a reflection across the x-axis. So that will cause our parabola to open downwards, but we also have a stretch by a factor of 3. Now, these can be combined into one go, right? So what this will do, this is both a reflection and a reflection across x-axis, and a stretch by a factor of 3, vertical stretch by a factor of 3. And all that will, the way that this will affect our graph is our original y values will be just multiplied by negative 3. Okay, so we're going to take all of our y values from up here and just multiply them by negative 3. Okay, so I'm going to come up with another table of values here. X and y. X stays the same. But then all our y values are multiplied by negative 3, so that's negative 12, negative 3. Vertex is in the same spot at 0, 0, negative 3, negative 12. But this time, we notice that our parabola opens downwards, right? So 0, 0, negative 1, negative 3, 1, negative 3. 2 and negative 12 is approximately there. 2 and negative 12 is approximately there. Okay, then we connect the dots. Okay, not so bad. Again, a little wiggly, but that's okay. So there is our vertical stretch by a factor of 3. So we can, again, just comparing these graphs, we can see that the new graph is quite a bit skinnier than the previous one. And we notice, immediately we notice the reflection, right? Instead of our parabola opening upwards, it opens downwards, okay? And then we do our translations, right? So we're graphing x plus 5. So that's 5 units left, 5 units left. And the plus 1 is 1 unit up, 1 unit up. So we're going 5 to the left and 1 up. So the left 5 units, that's going to take all of our points, all of our x values, and we're going to subtract 5 from them. And our translation 1 unit up, we're going to take all of our y points and just add 1 to them, okay? So again, I'm going to copy the table of values that we found in the previous step, and I'm just going to apply these two transformations. So let's apply those. all of our x values. I'm just going to subtract 5. So that'll be -7, -6, -5, -4, -3. And the y values, I add 1. So -11, -2, 1, -2, -11. And then I'm free to plot my new set of points here. So let's use blue. So -7 and -11 is right on the border here. -6, -2, so -6, -2, 5 and 1, and then we repeat the pattern on the other side. So our parabola is going to look something like this. Okay, not bad. And then, and of course, we notice that for y equals -3, x plus 5 squared plus 1, this actually tells us that our vertex is going to be at -5 and +1, which is exactly what we see when we consider the graph, right? We notice that our vertex is at exactly kind of where we'd expect it to be. And that is how you graph parabolas in vertex form. So I would say this is, I don't know what you guys think, but in my opinion, this is like a nice, easy way of getting a graph of a parabola. What do you guys think?
Yeah, good.
Nice. Definitely easier than like standard form. Remember going back to when we first started with quadratics, when we were making those tables of values, that seemed way harder just because you don't know what x values to pick. But here, you're not really picking x values. You're just always sticking with the same x values and then figuring out where those x values end up. So I think that makes it quite a bit easier. Okay. On to some word problems now. So as I've been mentioning kind of like throughout this, there's my mood, excellent. As I've been mentioning throughout this chapter, or throughout the quadratic chapters that we've been working on, quadratics actually come up in a lot of physics and chemistry applications, right? So in grade 11 physics, you're going to be covering what's called kinematics. And kinematics is essentially what this question that we're about to do is all about. So again, if you like this, you'll really enjoy grade 11 physics. Quadratics are also definitely present when you're dealing with equilibrium calculations in grade 12 chemistry. So you see that there again as well. But yeah, let's give this one a try. So for a high school charity event, the principal is dropping a watermelon from a height of 100 meters. The height in meters of the watermelon after t seconds is given by this expression right here. Now, this expression is kind of strange, but you often see this when you're dealing with, if you're throwing something and it's falling, you will see an expression that looks similar to this. Or I guess when you're not throwing it. This would represent when you're dropping something. If you throw something, then the expression is going to look similar, but a little bit different. So this is when you're dropping something. Now you might notice, well, the T stands for time, so that kind of makes sense. K is the initial height that you drop it at. But this G in the middle here, this G stands for the acceleration due to gravity, okay? So this is how fast an object will accelerate on Earth, or in a second, we're going to be talking about Mars. So in this case, this formula for Earth, h equals -0.5 times g times t squared, we are dropping it from an initial height of 100 meters. So that means our plus k is plus 100, because that's our initial height. Now this g, if we're on Earth, this is equal to 9.8 meters per second squared. And what that means is if you drop something on Earth, it will pick up 9.8 meters per second of speed every second. So after 1 second, you look at that object, it's traveling at 9.8 meters per second. You look at it again, it'll be traveling at, I don't know, 19.6 meters per second, and then so on and so on. It'll keep gaining the same amount over time. So that means this expression is equal to -4.9 t squared plus 100. Okay, because I just combined -0.5 times 9.81 gets you -4.9. Now on Mars, we might as well just do this because we're going to need an expression for Mars. Mars, the gravity is way less than that of Earth. It's approximately half. So on Mars, the acceleration due to gravity is 3.7 meters per second squared. Still quite a bit bigger than the moon. I think the moon is something like 1.6 something meters per second squared. So yeah, I think you guys saw that on your quadratics test earlier this week, right? Hit a golf ball on the moon. It goes much farther than it goes on Earth because the gravity is less. So this same expression for Mars, we have 0.5 times g times t squared plus 100. And in this case, our g value is going to be 3.7, which means our expression, what's half of 3.7? 0.5 times 3.7. I should know this. I should be able to do mental math, but it's Friday and it's early, so I don't even know where my calculator is. There we go. 1.85. So negative 1.85 t squared plus 100. Okay, so there are our two expressions. So we're kicking this watermelon off the roof, or we're dropping it off the roof, what have you. And so we're trying to answer a few questions based on these two expressions. So let's first just quickly plot these to see what they will look like. Actually, I think I had a plot for this. Let me just make sure. Okay, so I've already plotted one of these graphs. So this is the graph for Earth. Let's also plug in the graph for Mars. So h equals negative 1.85 t squared plus 100. Okay, so Earth is in red and then Mars is in blue here. So that's what our that's what the watermelon is going to do once it leaves the roof, right? And let's answer some questions here. So this is assuming that the principal is like hitting the stopwatch and the timer is starting right when he drops the watermelon, right? Now, what would happen if the stopwatch runs for 3 seconds before the principal lets the watermelon go? How would that change the graph?
Why would you do that?
What?
Why would you do that?
Maybe like there's two people timing it, like one person's timing, the other person is like dropping the watermelon. I don't know.
Right.
Maybe. But how would that change the graph? What would happen if he waited for 3 seconds before dropping it? Any ideas?
I feel like it has something. Oh, never mind. Go ahead.
No, go ahead.
Okay, so yeah, I think it's something. Maybe you'd have to like from the t, you'd have to minus or like +3 or something.
Yeah, I think that sounds appropriate. Leah, what were you going to say?
Well, I was just gonna say like that extra 3 seconds would change where the watermelon is, like at certain times.
Definitely, yeah. Like if we're waiting 3 seconds before dropping it, then it seems like everything will just get pushed back for 3 seconds, but then the rest of it will kind of remain the same. So I think you guys are kind of saying two of the same things. Ella, you're saying to our t values, let's add 3, and I'm kind of in agreement with that as well. And that'll change what's going on here. So let me propose something. So I'm going to open up some brackets here on my t expression, and I'm going to subtract 3. Okay. Now we know that this represents a transformation, right? When we add or subtract things inside the brackets on the t, what that's going to do is it's going to move our graph around, right? This represents a horizontal translation. And indeed, when I look at where my vertex is now, my vertex is at 3 and 100. Which tells me that if I were to wait 3 seconds, then the new vertex would be there, right? Because that's where the watermelon is being dropped, okay? So in this case, we can express that, this scenario, waiting 3 seconds, then dropping the watermelon. We can express that using a transformation, which is kind of cool, okay? So for part A, if we wait 3 seconds, our new expression will be negative 4.8 times t minus 3 squared plus 100. And of course, this represents a horizontal translation to the right 3 units. But because we're talking about a word problem, what this actually means in the context of the problem is we're just waiting 3 seconds to drop the watermelon. So wait 3 seconds to drop the watermelon.
Mr. Hopkins.
Oh, you can't see what I'm writing.
That's me, but I can't see.
There we go. Sorry, I just realized that. So that's what our new expression will look like. This represents a horizontal translation to the right by 3. And what that means in the context of this question is we are waiting 3 seconds to drop the watermelon. Okay, now we're on Mars. We're supposing that an astronaut dropped a watermelon from a height of 100 meters on Mars, and we want to determine an equation for the height of the watermelon on Mars. So we've kind of already done that because we plugged in the gravity into our height equation. Now let's go back to Desmos here. Actually, let's do this. Let's have them both open. Go.
Also, how did you get from 4.9 to 4.8?
Oh, thank you. Yep, thank you. That should be 4.9. Thanks. Okay, let's undo that transformation that we just did there. What do you notice about these two graphs? So the graph for Earth and the graph for Mars. What do you notice about them? How do they compare to each other?
Well, they have the same intersection point.
What was that, Owen?
They have the same like intersection, like vertex, I guess you call it.
Yep, they have the same vertex. Yeah, and why does that make sense in the context of this problem? Why do they have the same vertex?
Because it's plus 100, so that's the, the y-intercept.
Yeah, and that's, again, going back to the problem, that's the initial height of the watermelon, right? So we're imagining dropping the watermelon from the same height on both planets, right? But what do you notice about the shape of these parabolas?
Mars is larger.
Yeah, Mars is a little bit like wider, right? And looking at these two equations, so looking at specifically looking at the leading coefficient here, the negative 4.9 and the negative 1.85, we know that this represents a vertical stretch or compression, right? So looking at these two equations, it seems like Earth is being kind of stretched out a little bit more, right? Whereas Mars is not as severely stretched. Does that kind of make sense?
Yeah.
So in that case, we notice that, so for part B here, we notice that the parabola for Mars watermelon on Mars is wider, which means mathematically we can interpret that there's a larger vertical stretch in the equation for Earth. Right, so we have negative 4.9 versus negative 1.85. So Earth is a little bit more stretched out. It makes the graph a little bit more skinny, right? But Owen, your observation was correct, right? They both have the same vertex because we're dropping it from the same spot. So that's a similarity.
Yeah.
One thing we also notice is that actually the x-intercepts are different. So, or I guess the t-intercept in this case, right? These 2 points represent when the watermelon is going to hit the ground. So it turns out that dropping the watermelon on Earth, it'll hit the ground quicker than dropping it on Mars. It'll take longer for the watermelon to hit the surface of Mars. Right? Let's see what else we have. How will the graph change if the watermelon is dropped from 50 meters? What will happen to the graph?
You would change the I mean, like for the equation, you would change the initial height. So the plus 100 would just be plus 50.
Very good. Yep. And what does that affect on our graphs?
It moves it down.
Exactly.
Different y-intercept.
Different y-intercept, different vertex, moves it down 50. Exactly, right? Because now we're dropping it from half of the original initial height. Now again, the width or the stretch or compression of the graphs, those aren't changing, right? They're still reflected, nothing else is changing. The only thing we're doing is we're translating the graph down 50 units because we're dropping it 50 meters lower than our initial drop point. Okay. So that kind of word problem is a little bit more like we're doing some analysis on it. We're not actually like really calculating much, but those problems can be kind of cool, right? You have some sort of physical scenario, so dropping watermelons on different planets, and we're just using parabolas to kind of discuss how the motion of those two objects will change depending on the strength of gravity, which is kind of cool. So as I mentioned, if you have any desire to take physics, this is kind of the first month or 2 months of grade 11 physics, which is, I don't know, I like it, but I'm a little bit biased because I've been doing physics for a while. So physics is quite fun though. Okay, I have one more word problem. One more word problem and then one more quick little example. So the next word problem, actually already have the graph set up here. So let's change our x bounds, and then we'll read through the question together. So 0 to 130, and our y values from 5 to 10. Okay, so in this question, let's read through it here. Let's make this a little bigger. There we go. We're doing a little bit of research on fuel consumption. Okay, so a group of students are deciding to research the relationship between the speed at which you drive and the fuel consumption for a particular car. So essentially, I guess none of you, or you guys are all about to get started with driving, I would imagine, maybe this summer, pretty shortly. But essentially, there's a sweet spot that you can drive at where your fuel consumption is best, right? If you go too slow, then your fuel consumption is worse. If you go really fast, then your fuel consumption is worse. But there's a nice little sweet spot where if you drive at that particular speed, you're going to minimize the amount of fuel that you use. Okay, it's different for every car, but there always is that little sweet spot. And so these students, they collected a bunch of data. So I guess they drove at a certain speed, so 10 kilometers per hour, 20, 30, 40, so on and so on. And then they measured the fuel consumption in liters per 100 kilometers, okay? So they found when you're driving really slow, the fuel consumption is high. But then as you progress, the fuel consumption gets a little bit better. It seems like 80 is a tipping point, right? 80, our fuel consumption is at 5.8, which is the minimum fuel consumption. And then when we start increasing our speed beyond 80, our fuel consumption then goes back up, okay? Now, I plotted all of these points here in Desmos. Here, I'll turn off the height graphs there. I plotted all of these points, and you notice that it makes kind of like a parabolic shape, right? Now, our goal is to try to figure out an equation that models the relationship between speed and fuel consumption, okay? So for this, I want to express or find an equation. Let's say I have y is equal to ax minus h squared plus k, where x is the speed that I'm driving at, and I'm going to let y represent my fuel consumption. So ideally, I want an equation where, let's say you're driving at a particular speed. I want to be able to say, well, if you're driving at 72 kilometers per hour, I predict your fuel consumption to be blank liters per 100 kilometers. So that's the ultimate goal behind this equation that we're trying to develop. Now, because we're discussing vertex form right now, ideally it would make sense to, well, let's start with the vertex, right? We know that the vertex is at 80 and 5.8, right? So a speed of 80 kilometers per hour and a fuel consumption of 5.8 liters per 100 kilometers. And so this is going to represent our vertex. Okay. And the way that I'm going to express that in my equation is y is equal to a. I don't know what a is. A is going to be an unknown for me right now, but I'll try to find it. And then x minus 80 squared plus 5.8. And that will be the start of my expression in vertex form. Okay, so I just took my vertex and plugged it in to my h and k values. Right? Now, how can I find my leading coefficient here? How can I find my a value? Anyone have any ideas? So for this, what we have to do is we have to actually, you've already done something actually kind of similar to this. Going back a couple chapters now, I think. Remember when we were finding equations in factored form? I think you had one question for that on your quiz, right? What you do is you put in the x-intercepts first, and then you pick some other point on the graph and you plug it in. And when you plug in that point, it allows you to solve for the leading coefficient. So in this case, we are going to choose another point, choose a point, but that point cannot be the vertex. Okay, choose a point that is not the vertex. And we're going to plug in that point, and then we're going to see what our a value is. Okay, so I'm going to pick an arbitrary point here. I'm going to choose 50 and 6.4. We're going to plug that in, and we're going to see what our a value ends up being. So for y, I'm going to plug in 6.4 equals a. Don't know what a is. 50 minus 80 squared plus 5.8. Now I want you guys to really pay attention to how I'm going to solve for a here, because it is a little bit tricky. So we're still doing inverse operations, but just be a little bit careful. So I'm going to move 5.8 over to the other side. So I have 6.4 minus 5.8 equals a times, now 50 minus 80, that's negative 30. So I'll have negative 30 squared. So 6.4 minus 5.8, let's do that quickly. 6.4, oh, that's 0.6. I don't know why I'm not trusting my mental math today. I should just trust it. A times negative 30 squared. 0.6 equals a times, so negative 30 squared, so that's 30 times 30. That is 900. So a is equal to 0.6 over 900. So a really, really small a value. So this a value is equal to 0.000 and then 666 repeating. Okay. So therefore, our final expression is y equals 0.000666, and then x minus 80 squared plus 5.8. Okay, and let's see how close that ends up being. So let's actually plot this. Y equals 0.000666 x minus 80 squared plus 5.8. Let's see how close we got. Okay, not terrible, but also not too great, right? Like I'm hitting a lot of points at lower fuel consumption, but then I'm kind of missing a lot of the points up here, right? Now remember that we can actually have Desmos find an equation for us. I know we mentioned this very briefly when we were discussing, I think I mentioned quadratic regression, right? Do you guys remember that a little bit?
Mm-hmm.
A couple chapters ago. So when we use regression to find that a value, it actually finds a slightly different parameter. It finds 0.00750969. So it does fit a little bit better at the higher end, but it's still kind of off on these guys, right? So data in real life, data is not perfect, right? Especially when we're dealing with like cars and fuel consumption. It's sometimes the data that you end up getting is really scattered. It's not the greatest. It's not the most uniform data set. So that's why we definitely get differing answers when we do it kind of by hand or when we do it with regression. And in both cases, the fit isn't that great, right? We're still missing a lot of points here. Okay, last exercise here, and then we are done for the weekend, which is kind of nice. So we want to figure out the equation of this parabola in vertex form. Now there's some nice steps for this. So step 1 is find the vertex. Okay, so in this case, my vertex is at -2 and 6. So -2 and 6. And now what that allows me to do is it allows me to write out kind of the framework of the expression. So we will have y equals, I don't know what my a value is, but I know this will be x plus 2 squared plus 6. Because again, my vertex gets translated perfectly into vertex form. And then what I'm going to do is I'm going to identify one other point on the graph here. So it seems like this seems like a pretty likely candidate. So -1 and 3 seems like a good point. And I'm going to plug that into a and y. So 2 plug that in for x and y and then solve for a. So plug in another point on the graph. So we have 3 equals a times 1, -1 plus 2 squared plus 6. And then I'm just going to solve for a, right? Solve a. So 3 is equal to a, -1 plus 2 is 1 squared plus 6. I'm going to move the 6 over to the left side. So 3 take away 6 equals a times 1 squared, so that's just a. So a is equal to -3. And then we conclude, right? So therefore, y is equal to -3, x plus 2 squared plus 6. And that's our equation. Okay, any questions about vertex form? Does anyone want to see like more examples, or was that a good introduction for it?
That was good.
Good. Okay. Cool. With that, I think we're finished for today. Now I am going to be doing. Actually, let me program that in right now. I'm going to be doing a quick homework check. So let's create that right now. So homework check for the week of May 25th to May 29th. Okay. So that includes today's stuff as well, like main focus on yesterday and today because that's the newer material. But same as we did last week, right, for the midterm check. I just want to see that you guys are keeping on top of it, especially because we're getting towards the end of the term, and I mean you already have your final assessment, so I just don't want you guys to get overwhelmed. That's the ultimate goal here. So make sure you're sticking on top of your homework. I'll do a quick poke in. Again, it's not for grades or anything. I just really want to make sure that you guys are keeping on to it. Okay. So I'll assign that. We'll make it due for how about Sunday at 11:59 p.m. and then I'll do a check Monday morning. And if I feel like you're not doing enough homework, I might have comments. I'll look at both the midterm check that I did as well as this current check. If you didn't do so good on your midterm homework check, but you've shown me that you've done quite a bit of homework for this stuff, then I'll applaud you for that. But if I find that you're lacking in both the midterm check as well as this week check, I might have some critical comments for you. Okay. So please get that in by Sunday evening. All right, and I'll take a quick look. Other than that, guys, that's it for me. So it's up to you. If you guys want to stick around, feel free. If not, have a great weekend, and I'll see you on Monday. Okay?
Thank you.
Bye, guys.
Bye.
Hey, Hamza, I just saw your message. Yeah, I mean, you have an opportunity to complete some homework now, right?
Yeah.
So yeah, take some time. Try to go through a few questions. I'll still be around. I'm just going to leave the meeting open. So if you want to ask some questions about the homework, just let me know. I'll be here. Okay.
I think I'm seeing my tutor. I think on Sunday or Saturday.
Okay.
Would it be possible to do the homework then and then send it to you then?
Yeah. As long as it's in before Sunday, I'm going to do a check Sunday